Do you know this person?
All right, so we're back on the air, so to speak. Let's see. All right, so project 4, right? So project 4, I made this due about a little over 2.5 weeks from today. So this is somewhat involved, and it's important to get an early start. And we don't have a lot of leeway on this due date because we need to do one more project after that. And so this is, in a way, a very simple device. So it's kind of in this category of implementing in software something that you would normally have as a hardware device. And so it's a very simple timer, just a countdown timer. So it's kind of an extension of the click counter, so that kind of UI, almost the same kind of UI. And it has a 2-digit display and one multifunction button. So unlike the click counter that had 3 buttons, this one has just one button, and the functionality of the button is state dependent. And so in the context of this project, we'll talk about a little more about state machine diagrams and using those for modeling behavior. So let's first discuss the behavior, and then we'll transition into this group activity in a little while. I also wanted to give a little bit of an overview of the stopwatch example. But so let's go through this briefly. Then let's look at the stopwatch example and the state diagram. State pattern, and then transition into the group activity. Okay. So basically, think about it as a very simple device. The double-digit display and the button. Okay. So the timer always displays the remaining time in seconds. Gotta add that, right? So that's it. I don't like imprecision, so we're gonna add that. Oops. Okay, that's better. So that is an invariant, so to speak, in the requirements. So display always shows the remaining time in seconds. Initially, so when you insert the battery or plug it in or power it up or whatever, that corresponds behaviorally to the initial state. It is stopped, and the remaining time is 0. Now what you can do is, you can start pressing the button, and it'll, kind of like the click counter, it'll increment the remaining time. So if you keep pressing the button repeatedly, it'll count upward. So that's this one here. And if you now just let the device sit for 3 seconds or more, then it starts counting down. All right, so that's how it transitions from the mode where you're setting the time to the mode where it's actually counting down in seconds, right? So that's the 3-second elapse. So in other words, we're transitioning from a very simple behavior like in the click counter that unless you interact with it, it won't do anything. Here we have a behavior that has a dimension of a timeout, meaning even though you just stop interacting with it, after a certain timeout, it might do something on its own. All right? So it's all part of the learning roadmap, so understanding and dealing with and implementing timeouts. Non-trivial. Okay. So while it's running, it'll count down, reducing the remaining time by one count every second. Okay. And while it's doing the countdown, you can cancel the countdown by hitting the button. Or if you never hit the button while it's running, at some point it'll reach 0 and then it'll start beeping. And then when you hit the button, it'll stop beeping. So in every mode or state, whatever you want to call it, the multi-purpose button has a specific purpose. All right? And so the purpose is what you could call state dependent. Also, there's another possibility where if you're going up to the maximum of 99, let's see, then it'll start counting down immediately. Also, because that's the maximum. I think it should say that somewhere. Oh, okay, no, forget about that. We don't need to make it more complicated. Simply, if it hits 99, it won't respond anymore to attempts to increment it. And it'll start counting after 3 seconds. That's a cleaner and simpler behavior. So again, the goal is always to keep things as simple as possible while satisfying your functional requirements and also the non-functional requirements. So in fact, keeping things simple is, at a very abstract level, a non-functional requirement. So, do these requirements make sense? These functional requirements? Just imagine a very simple device. It just sits there and says 0. Then you can repeatedly press the button. It'll increment whatever it displays. When you reach 99, it won't let you increment anymore. And if you wait 3 seconds between, or if more than 3 seconds go by, 3 or more seconds after your most recent button press, it won't let you increment anymore. It'll start counting down. But if you hit the button while it's counting down, that cancels the current countdown, and time goes back down to 0. Okay? If you don't cancel it and it reaches 0, then it starts beeping. And it'll continue beeping until you hit the button again, and then it'll stop beeping. Okay.
What is the last thing the timer handles rotation?
Very good. That's an Android-specific requirement. So you will see, when you, so in the click counter, we'll pull that up. It's a device rotation, and there's some links about this further down. But so I've updated this, because all of this stuff works now. I'm going to work on getting Stopwatch into a usable Gradle-based state over the next few days, and I'll keep you posted. So both the click counter and the Stopwatch examples are going to be very useful and crucial, basically, for your ability to make progress on this project. So now, let's take a quick look. Main. Android adapter. That is there's an example of playing a notification sound. You can use that kind of stuff, I guess, for the beeping. Let's see. Here it is. So when the device is rotated, the Android runtime automatically invokes the onState instance state method. And it passes an object. These bundles are objects kind of like a persistent map, kind of like that. So it basically gives you a chance to save information, because when the device is rotated, it'll basically restart the app, meaning you lose everything that you've done unless you implement these methods correctly. Okay, so what do we do here? What's really the one thing we want to store? Well, the way this app is architected, the model is actually an object. So we're storing the entire model object as opposed to just the integer counter value. And we can do that because so things have to be serializable. Java has this mechanism for storing persistently any binary object or any object as kind of a binary file or string. And the only prerequisite is the object has to, or the class has to say, I want to support serialization by implementing the interface serializable. So let's go to model. I'll show you that. Model, default bounded counter. Oop, it doesn't say it. Fair enough. So this one, the interface says it. Probably a poor choice to put serializability in with this interface. It should have been maybe an implementation choice. But then maybe this would have required a cast. There was some reason I didn't like this. All right, so in other words, this is not just the counter value, this is the entire model state, which in this case is just a wrapper around the counter value. But you can basically store an entire object in the bundle. You can store multiple objects in the bundle. See, so the string is the key, so it's basically a key value map with the keys being strings and the values being pretty much arbitrary things. And when the device rotates, so there are a few steps, right? So you take the device, okay, when you rotate it, this method gets called. And then that method gets called. So this gets called, the app gets restarted, and then that one gets called. And then there you get to restore the model. So here you say, well, and you have to invoke the super method somewhere. Otherwise it'll complain, the inherited version, because it might need to do more stuff. That's how frameworks work. So then here it says, okay, let's retrieve the object stored as a string key, and it'll automatically deserialize it. But then, just like in maps and Java collections before genericity, here genericity will not help really, because these things are managed by the Android environment. So you basically get an object, a serializable object back. So you have to cast it back to counter, to whatever you put in. All right, so this handles device rotation. And that's the long answer to your short question about this requirement. All right. So there are a bunch, I'm a stickler about non-functional requirements. I mean, that's, after all, one of the main learning outcomes of this course, to appreciate and pay attention to non-functional requirements. So that's there. And then there's some of that stuff. Then there's written part where you can reflect, and that also includes the documentation. Right. So the group activity that we're going to do we're going to start during the last 20 minutes, that should be included here, part of the doc folder of the project. Okay. And then the other stuff is really about the journey. All right. So you'll become acquainted with this over the next few days, I'm sure. I wanted to basically show you the stopwatch example, and in conjunction with that, the state pattern. And that's going to be useful for this. So for the modeling itself, you can refer to some of these links and examples. And of course, the corresponding chapter in Uncle Bob's book, right? So there's a chapter on, there's actually a whole multiple chapters of the book on the UML modeling notation. And one of the chapters is about state machines. So that could be your reference, but there are these additional references here. And again, modeling, the idea is not to get bogged down in details, just to kind of keep things as simple as you can while being as expressive as you need to express your understanding of the requirements. So when you look at, and in behavioral modeling, you obviously focus on the functional requirements. The non-functional part is what happens when you actually start putting stuff in code and all that. But the behavioral functional requirements, the kinds of things you'll want to ask yourselves when you start this activity. How many states do I need? Which states are there going to be? What are the transitions going to be? And one useful piece of notation is you can represent a timeout just as a label of a transition. So you can write something like this. So here, 3 sec, and then guard and action. So this is a timeout, meaning that the 3 seconds elapsed, that's not the user pressing a button, that's 3 seconds after having entered the state. So in this way you can express the timeouts quite concisely and nicely. And timeouts are so common. You've seen this. So this device, you can think about this as being maybe a piece of a more interesting device such as a microwave. And a lot of microwaves get used a percentage of their time to heat stuff, and another maybe significant percentage of their time just as a clock to look at or the timer, right? So this could be the timer that's integrated in the microwave. All right. So any questions so far? It's going to take some time to sink in, So that's why I'd rather start looking at the stopwatch code, and again, so it's not in a runnable state, but that's really outside of the code base, outside of the Java code. That's just me doing a little bit of Gradle conversion. It's a lot of stuff that I have to do. Some of you already know this in more detail. Certain things don't take a lot of time, but I have to be able to sit down and focus and just work on them, without all these other things I have to basically deal with as emergencies or semi-emergencies. So, but things are improving, so that's good. Or maybe that's just me being optimistic. I say things are improving. Okay, so let's check it out. So there are two things really architecturally or in terms of patterns I'd like us to get out of this example. And now I just remembered something I wanted to say about the click counter and the testing. So I think I was, so we ran out of time, and I was able to talk a little bit about the X-unit test patterns. And what I think I might not have done explicitly to tie that to the click counter example. So the key point is that in the click counter example, the way we're using, so let me pull that up. So if you're looking at the actual test code here, so here's the roboelectric one, and then there is the one that, for reasons I haven't actually understood yet fully, it has to do with the dependencies. I just don't yet know how to solve it. So there's the abstract activity test. So this is what in the X-unit test patterns called a abstract test superclass. And what we're seeing here is the result of a refactoring where we might have had code duplication of the test code before, and we pulled it out into a separate class. And the roboelectric is a concrete test subclass where we just say, okay, we'll extend that common test superclass, and it pulls in all the tests. And we just need to customize it a little bit so that the tests will work when run using roboelectric, meaning with the simulated Android environment, the kind of these fake Android classes as opposed to the real emulator or the even more real device. Okay, and so this is one concrete test subclass, and then the other one was really the wrong example. The other one was, let's see. Remember how the other one was the Android instrumentation test, and there we had to, because we can have only one superclass, and we used up that slot, so we did talk about this briefly. That's why every method, so the abstract test superclass kind of broke down here a little bit, because every method that we would have liked to inherit from this abstract test superclass, we have to have a forwarding method for it here. So let's say if the abstract test superclass had 100 test methods, here we have to write 100 of these forwarding methods. So there it might be better just to do something using reflection, where we might say, okay, let's discover what methods this class has and then invoke them programmatically at the using the Java reflection API. It's kind of like having our own little test runner that allows us to run the instrumentation test in conjunction with an abstract superclass, test case superclass. So, but that, that's a kind of more advanced technique. So here for this, the example with just these very few test methods, forwarding methods are perfectly adequate. I would say even if you have 10 or 15 of these, it's fine. But if you go above 50 or 100, then it becomes so easy to forget one of them that it's actually not recommended. Okay, I just wanted to make sure I emphasize that point about the test case superclass as a very common X-unit testing design patterns. Okay, so now here in the stopwatch, there's also, let me see, there is no roboelectric here yet in the stopwatch, I believe. Yep, but there are other interesting kinds of tests, and we'll see those. So right now, so architecturally, the two pieces I want us to take away from stopwatch are the state pattern as a way to take a state machine, this kind of thing, and kind of express it in a way that corresponds very directly to the conceptual state machine. Okay. That is one piece. The other piece is how we're architecting the kind of the high-level architecture in layers. So you might have seen or heard of in other classes or in other contexts or at work or wherever, you might have seen these architectural patterns for user interface-based applications. So there's a whole list of these. And the original one is Model View Controller. And Model View Controller assumes this kind of separation between view components and the controller components in such a way that the model pushes updates directly to the view. Okay? Whereas in Model View Adapter, it's more like the kind of layering that we have, where we have this activity in the middle, and we have the view components above, and then the model components below. So the model is just basically our UI independent behavior. Like in the click counter, it's just the part that we store for device rotation, for example. So well, actually, let's look at Model View Controller first. And then there's also Model View Presenter, to make things more confusing. And then there's Model View, what's that other one called?
It's like Model View Controller.
View something, right? Yeah, Model View Controller.
View model?
Oh, yeah, Model View Model. Right, so there's a never-ending, there's this kind of proliferation of these different kinds of variants, but the main ones to understand, in my opinion, are Model View Controller and Model View Adapter. And in Model View Controller, what you see is, so the user sees these view components, in other words, information. This is the direction in which information flows. So information flows from visually from the view component to the user. So user sees those, receives the information. User interacts with a controller, such as pressing a button or so. Controller invokes some methods that change the model, such as incrementing the counter or something like that. And then the model says, I have changed. And then the view that is subscribed to these changes as an observer. So what you have here usually is kind of within the model view controller architecture, a little observer pattern. So the view changes to reflect these recent changes in the model. So to tie it again to the click counter, so let's say user presses increment button, controller invokes an increment method on the model. Model says, I have changed. View says, oh, I better get updated values from the model or the object I'm observing. So it says, okay, what's the new value? In this case, just the counter value, but it could be a much more complex model with a much richer view. So it gets that and then displays the updated counter value to the user, and then the thing goes full circle. All right? So that's model view controller in a nutshell. And you see how the model pushes changes directly to the view. So by contrast, model view adapter, this doesn't have a drawing, so that's almost useless, but there's a very nice, if it's still there, okay, nice, the nice blog post here. So this is a really good blog post in my opinion. So here, because it also talks about teaching, etc. So in undergraduate CS programs, MVC is taught as an off-the-shelf pattern, explained once and then ready for use in the real world. So I'm going to go a little beyond that. That's why we're looking at model view adapter. And here you can see the two next to each other. And now, why are there solid arrows and why are there dashed arrows? The solid arrows are method invocations. Just ordinary method invocations. Right. So just like we said, okay, this is MVC. Controller, let's say, okay, user interacts with controller. Let's say increment button press. Controller invokes a method on the model and then pushes a notification out, and the view is a component that's subscribed. So that's a notification, and this is an ordinary method invocation. So notification meaning like event-based. And what does that mean? Well, it really means something like the button having the button being able to notify other components of the fact that the button was clicked. Like the on click that we looked at. So when we looked at that in the graphical UI editor. So we saw that there's an on-click property in the button, and we could set that to the name of a method. And that's the listener method, and that is this kind of arrow. Or this kind of arrow will show up like in Android. Okay? And there are many other ways it can show up like. But this is kind of the most prominent way in Android. We're about to see another way also. Okay. And again here, the view might be told, okay, the model has changed, and then it might go back to the model, give me some more information. So this is again an ordinary method invocation, or possibly multiple method invocations. The thing is, so this is a triangle, and it's characterized by the fact that the model notifies the view directly. But in Android, it doesn't really go like that. So in other words, what they just said up there is actually correct. You cannot necessarily put this to direct use. So if we look at our click counter, it's a lot more like this, because So the view in this case comprises both buttons and text fields, for example, where the value is displayed. All right? And what characterizes these things that are in the view? Did we write any code for them? Did we implement them, or did we just take them off the shelf, so to speak? Like, did we place them in the visual editor? We did that, right? We just say, okay, here goes the button. I mean, I did that before, right? But it's there. You could see it in the visual editor. So there are a bunch of buttons and a text field. You know, so these are completely standard off-the-shelf components. So these are in the view. Or you could say, well, this is kind of a view controller combination. You could even make that argument. And then when the user presses the button, the on-click thing happens here that I was just describing. And the listener method in the adapter gets invoked. Then the adapter talks to the model, and then the model might push change notifications back to the adapter. So in other words, there is no direct connection between the model and the view. So it's properly layered, you know, bottom, middle, and top, which is actually an advantage potentially. And yeah, then the adapter will invoke methods in the view, such as updating the display value and that sort of stuff. So the flow of information will be this dashed arrow, like an 8, right? Then this solid arrow, then back through here, optionally, and then back here. So kind of like that's why I call it like an 8. Okay. So let's actually see this in the code. And yeah, I'm thinking, you know, maybe it's more beneficial if we leave the group activity for next time. In this way, you can look at the group activity, kind of start doing it ahead of next class, and then we won't need as much time. You can basically just use it to compare notes mostly with people from other teams. So in other words, I'd like everybody to, and the group activity is posted on Piazza. So what I'd like everybody to do is, every team should start to work on the group activity as the team, meaning the state-based modeling. And then be prepared by next Wednesday to kind of compare notes to validate your model by talking to people from other teams. Does that make sense? I think that's going to flow a little better, so that I can get you up to speed with some of these other important things. You know, so here we have basically these architectural patterns, and we can observe those. Again, you know, let me pull up the click counter. And yeah, maybe it's easier to browse the code in Android Studio. Okay, so if we go to the main layout, again, that's in the resource folder, in the res folder. So basically, so this is the view, and you will see just these completely standard components that are about to pop up. If this works out. I mean, you remember, right, the text field with the current value and then the three buttons. So we don't need to wait for this. And, okay, here they are, right? So if we select this, here it just tells you, okay, this is a text view. We select this one, it says it's a button. You know, it has these standard properties. That's all based on the Java Beans convention, which has been around for a long time. Okay, how does this get connected to the adapter? Meaning, how does this connection get put in place? The dashed arrow here. And that's the on-click property of the buttons. So if we select a button, then you see here the on-click, and it says, so this you probably can't read, so this says on-click, and here it says on-increment. And where is that on-increment method? Well, that's the method in the main activity. So the main Android activity plays the role of the adapter. And it's right there. So on increment, and here's the solid arrow with the model, this other piece, right? So model dot increment, that is this part, okay. And then here we don't have, well, we don't have the dashed arrow coming back from the model in this simple case. In the stopwatch we do. And then we have the update view, which is this part. The arrow from the solid arrow from the adapter back to the view. And now I'm supposed to be able to find this. I don't know how to do it. Oh, go to, yeah. Go to. Declaration. There we go. It's just right here. Okay. So here we have anything where we say find view and then talk to the view components, such as here, setting the text. That's an example of the solid arrow from the adapter to the view, to a view component, where we're invoking a method. All right. So this is how the pattern is manifest or reflected in the code, and that you always see these kinds of things. So in a way, you know, there's this. These are two views of the same thing. Ultimately, the main source of truth is the code, and your diagrams, they're supposed to be an accurate description of the code in a much more abstract way. But that's the sense in which they're helpful. But anything that is represented in the diagram, there should be some equivalent in the actual code. All right. So simple example. Let's now move on to Stopwatch. And in Stopwatch, you have several packages. So there's model with these various sub-packages. Then there's a common, and there's a reason why that stuff is in, why this common package was created. And then there's the Android one here. So this is the Android activity, and basically, okay, well, I have to tell you briefly what this Stopwatch app does. And as you can imagine, this is just a simple stopwatch with a 4-digit display. What does this? Maybe it also has only 2 digits. No, let's see. I think it has 4. Let's take a look. Yeah, so this has seconds and minutes, you know, so it does deal with ultimately it needs the four digits. So 10 minutes, single minutes, colon, tens of seconds, and single seconds. So there are your 4 digits. Okay. So the UI, I'll just draw it. Okay, so the display, and then there's a start-stop button and a lap reset button. So this is the UI of the stopwatch. Nothing more, nothing less. You're very simple. And the way it works is, well, you can obviously hit start-stop, right? So you can describe the requirements in a similar way as the ones for the countdown timer. So it starts in a stopped state, and the time so far is 0. And then you hit start stop, and it starts keeping track of the time. So it starts actually incrementing. And then you can, for example, hit start stop again, and it stops. Then you hit start stop again, and it continues where it left off, right? And if you're in the stopped state and you hit reset, it'll reset, and you're still in the stopped state. And let's see. I wonder if there's. I thought I had a stopwatch. Some kind of state diagram ready that matched this one. Maybe there's some examples here. Oops. Yeah, I don't have a link for this stopwatch. Let's see. Because I know there is one somewhere that's very similar to what we have here. Some of these are very complicated, but they emphasize other stuff. Yeah, there we go. This is kind of the closest here. Okay, that's good. Yes, this is the familiar one. So, yep. I remember now. So, oops. Is it page? I'll put this in here. Okay. Yeah, there we go. That's very close, right? So you could model it like this. You could say, okay, you're in the stop state. You might wonder whether you really need a reset state with the spontaneous transition back. You could just say reset, and the action is to actually reset the timer value. And then you have basically stop and go. So you can go. And in ours, the go and stop are one button. So again, buttons have state-dependent behavior. And then here there's the lap, and again, pressing lap puts you. Pressing lap means you're freezing the time that's being displayed, but internally you're continuing to keep time. And then you can return to the current time that's being tracked, or you can go from lap to stop, and then if you press let's see, then you're looking at lap time, and internally you have a time that's further along, but it's also stopped. So then you could go from here back to the stop state and look at the actual time that you've stopped so far. And then if you press that button, if you press the reset button, then it'll reset the value to 0. All right. So that's why, I mean, that's the dynamic behavior, and then you just need basically the variable for keeping track of the time. But there's a little bit more complexity in the sense that you need to, depending on the state, keep track of the clock ticks, so that when a clock tick occurs, you're actually incrementing the internal time value, and you're, if there's a display, so that's kind of outside of the dynamic model, but you're updating the internal clock time as you're receiving these tick events. So meaning that a more complete model would pay attention not only to the external button presses, but also to these internal timer ticks. So the way the stopwatch example is architected, the 3 model components are a passive time model, and this is architected in such a way that pretty much for everything there's an interface, and you could basically plug in different implementations to facilitate testing. So it's very much built in the spirit of Uncle Bob's serendipitous architecture section. So we can just look at the implementations, and as long as you're aware that there is an interface pretty much for every implementation. So here we can just make these changes to a current time value. So this keeps track of running time and lap time, and you can reset, you can increment, you can look at the current runtime, or you can say, I want to take a lap, kind of a snapshot of the current time, that becomes your lap time, and then I want to look at the lap time. Okay, so, but you see that this is a passive model. It only exposes these methods, and it doesn't have any kind of internal activity like incrementing itself or so. So that is a separate concern. So this is only the equivalent of the click counter value, without any other behavior. Then there is an internal clock, and there's some interfaces here, and those are, we'll get into some of the details next time in conjunction with a demo. Just to get you started though, basically we have some of our own listener interfaces, which are kind of observer interfaces. So the clock model, is basically just an observable source of ticks. So meaning this has control methods, which are start and stop. When you tell it start, it starts ticking. When you tell it stop, it stops ticking. How does that work? Well, there's something called a timer task. So these kinds of things are platform or framework specific. Android has these timer tasks that are, these are Java timer tasks, right? Yeah, so that's good. So Java has improved a lot. So these are Android independent timer tasks. So Java has this timer task class where you just implement the run method, and the run method is the method that gets invoked every time the timer basically ticks or fires. Okay, and you can specify whether you want the timer to be a one-shot timer, meaning once it elapses, it invokes the run method once, and then it's gone, and you cannot reuse it. Or it could be a periodic timer, which will repeatedly invoke the run method, and you specify the initial delay and the periodic delay. So they could be different. They don't have to be different. But you get to specify both of them. So the way this timer task object works is you specify what happens every time the timer should beep or click or tick, right? So every time, or once, or either once or periodically what it should do. So that goes in the run method, and then you just specify the initial delay and the time period in milliseconds between two consecutive ticks of the timer. And basically what we're doing, just like when you press, and this is the observer part, and here you'll want to pay attention to the similarity to the observer pattern when you have a button and you're connecting an object to the onClick method of the button, and that onClick method is invoked every time the user presses the button, in the GUI. Every time the user presses the button, then whatever method gets connected to the onClick, so in the case of the click counter, it's the onIncrement. Just like that, the timer, every time the timer ticks, so to speak, this run method gets invoked, and we're setting this up so that it invokes the onTick method on some listener object. So the only difference really between the button and this little timer component is the button only invokes the listener method, meaning in this case the onIncrement or onDecrement, depending on which button it is, whenever the user triggers that event, whereas this timer is an internal thing that you can say, okay, let's start this timer component, and when it's running, every second it'll invoke the run method, which abstractly is like saying tick, and there could be another component that's receiving the ticks. Does that make sense? Just like the click counter adapter was receiving the button presses, here we're going to have a listener component that's going to receive the timer ticks. And guess what it's going to do? What does that component do when it receives a timer tick? Well, in the context of the stopwatch, it's going to increment the internal time value. And where was that? Well, we saw that here, right? So there's this dumb time model. Okay, so we have an instance of this, and the running time is here. And whenever the timer says tick, we want this inc runtime method to be invoked, right? So that the internal timer or clock value goes up. And here we have this clock component that sends out the ticks. So what's the missing piece? The missing piece is basically this thing here, right? Because this will say, oh, when I'm entering the go state, I'm going to start the timer, and I'm also going to listen to the ticks, and when I get the ticks, I'm going to increment the dumb time model. And then if the user presses stop, I'm going to go back here, and as part of this transition, I'm going to stop the timer component. And there are no ticks. So this model ties everything together. So these things have to be connected. And the model is the part where you can use the state pattern. So just as a preview, we'll obviously continue next time. So you can kind of see that for every state in that diagram, there is a little class here representing that state. And that's what I meant earlier by state pattern. So if you research the state pattern a little bit, there's a chapter in the Uncle Bob book. There's a lot of literature on this. There's some references here. You will see the significance of the state pattern. But so what we have here is a state pattern-based implementation of a state machine like this. And state pattern is obviously not the only way to do it. It's also not particularly simple, but it's particularly close to the actual state machine. That's why it's useful here. And so we have a much richer and complex model for the stopwatch. And we haven't even talked about the activity and the views, right? I mean, the views we talked about. And then the activity is basically, again, the adapter, except that unlike click counter, where the model was really extremely simple, here we have a much richer model, and the project 4, will be, maybe a tiny bit simpler than the stopwatch, although it does have something that stopwatch doesn't have, which is the timeouts. Okay, but architecturally it's very similar to stopwatch. So really the key is to start understanding the stopwatch in as much depth as you can. So do that, then do the modeling, and as the group activity, and look at the state pattern. So that's pretty much it. Great. So, see you next time. Keep discussions going. I think now we're going to have a lot of discussions because we're taking things to another level now.